Okay, so yesterday I introduced the notion of 1 pi effective action, so that will be the major player today. So let me write down the expression for the 1 pi effective action. This was the structure we found, okay, and this we had defined in terms of the regular vortices. Okay, so this is, you see that this is a single curly bracket, which means that this is the 1 pi vortex and not the elementary vortex. Okay, and even though I'll be working with this action, it should be kept in mind that all that I'm doing, okay, can also be done with the effective 1 pi action, which means that you have to put a subscript E over here. Okay. And that effective 1 pi action corresponds to integrating out all fields outside a certain subset, which is called 1 minus p, okay, and then integrating out all fields, all other fields in the loop. Okay, so 1 pi effective action basically keeps all fields at the level of tree level propagator, okay, but integrates out everything at the loop level. Okay, but 1 pi effective action after integrating out the massive fields means that for the massive fields you integrate out both the tree and the loop contribution, right? That's the reference. So if in particular, why this, so this as written, this psi and psi tilde are infinite component fields, okay, but if we restrict to 1 pi effective action after integrating out a subset of the fields, we can have psi and psi tilde finite dimensional fields. Okay, so let me write that down here. Yes.
The algorithm to write down the psi tilde the psi brackets to the end.
Yeah.
Is to start with the double bracket.
Yeah. So that's one way, that you start with the double bracket.
And then write down the 1 pi diagrams.
Exactly, and add them up. Okay.
Add them up. So that would be one algorithm.
Yeah, but that you can also interpret as it as an integration over a subspace of the moduli space, because after all each Feynman diagram is integrating over a part of the section, right? So the alternative algorithm will be to identify the section that corresponds to that section segment that corresponds to the sum of all the 1 pi diagrams, and just integrate the off-cell amplitude over that section segment. That way you can define it directly in terms of the Riemann surface, right? Instead of having to go through this algorithm of first defining elementary vortex and then building up the 1 pi vortex. So both are equivalent, because you just go from one to the other by standard manipulations. Okay, so what will change if we have already integrated out certain subset of the fields is that we will put some projection operator P over here. Okay. And of course this interaction term will be different, but that will contain exactly the same information as this one, okay, provided you restrict your external states to be P invariant. Okay, but for now let me just work with this one. So from this one can write down the equation of motion, 1 pi equation of motion, and those take the following form. Okay, where we had also defined this bracket. for every phi r. Okay, so this basically defines the state. So these are the two equations of motion that you get by varying this 1 pi action. So now the first task in this approach is to construct the vacuum solution. So vacuum solution, okay, which I'll call psi vacuum. Okay. This is not necessarily trivial because as we discussed yesterday, okay, there is a term, see naively you would think that psi and psi tilde, setting psi and psi tilde equal to 0 should solve this equation. Okay. But that is not true because this sum over here, okay, starts from 0 to infinity. Okay. So the n equal to 0 term, this is a constant piece. So psi equal to 0 and psi tilde equal to 0 is not a solution to this set of equations, okay, because there is a non-zero contribution from here. Okay. So you really have to look for the vacuum solution. Okay. Now the vacuum solution means that we restrict to k equal to 0, 0 momentum sector. Okay. And just for simplicity, we will also restrict to the NS sector. Okay. In heterotic, of course, we have to restrict to NS sector because the Raman sector is fermionic, so it doesn't make sense to have a vacuum which carries fermionic quantum number. But in type 2 string theories, for example, you could also switch on RR background, Raman background, because those are bosonic fields. Okay, but let's now stick to heterotic and look at the Lavoisier sector. Okay. So in the NS sector, of course, this operator G is just identity. Okay. So we can get the solution by setting psi tilde equal to psi. Okay, that solves the first equation because G is identity, and then the second equation becomes QB psi. Psi back. Okay. And now the idea is that you can try to look for a solution to this equation in perturbation theory. Okay, because this term, for example, has a perturbation expansion in powers of G string. Okay, so you can first look at the G string equal to 0 case. Okay, in which case you just have to solve QB psi vac equal to 0. So to 0th order, you just take the solution to be 0. Okay, and then you can try to build up the solution in perturbation theory. So there are three kinds of possibilities, okay, roughly. Okay. The first one is that no massless tadpole. Okay, which basically means that this bracket, okay, for the n equal to 0 term of this bracket, this is a non-trivial state, but this has no component in the massless sector. Okay, that's what one means by absence of massless tadpole. Okay, that a linear term exists, of course, for general string field, okay, general string field component, but not allowing the component which is massless. In this case, typically psi vacuum can be constructed as power series in GS square. Okay, and I'll just illustrate this by a simple field theory example. Okay, so suppose you have a potential, okay, where the field has a mass term, half m square phi square, and then there is a linear term, okay, but the linear coupling starts at order GS square, say, plus higher order terms. Okay, and looking for solution to equation of motion in this case corresponds to solving for v prime phi equal to 0. Okay. And you can easily see that the v prime phi equal to 0 has a solution at phi, it starts at minus c g square gs c over m gs square plus higher order terms. Okay. So the first term is of order gs square, and then there will be order gs to the 4 correction and gs to the 6 correction and so on, because this term over here has an expansion in powers of gs square. Okay, so this is the simplest case. So the second case, which is in fact more interesting, and that's where the string field theory is really necessary. Okay, because in conventional perturbation theory you cannot really deal with such cases. Okay. And this is where the massless work-upon function is not 0. Okay. But this massless field is not a moduli field. Okay, which means it has a potential. So in this case, one can show that psi vacuum has an expansion in power of gs, or in general gs to the alpha for alpha less than 2. Okay, so this is in favorable cases, and I'll explain what I mean by this. Okay. So the point is that in this case the expansion is no longer in powers of gs square, okay, which will be the standard perturbation theory. Okay, but the expansion will have a power of gs that is less than 2. Okay, and the simplest example is when the expansion is in power of gs. Okay. So again, it's best to illustrate this by an example. Okay. So here we are considering massless case, so there is no mass term. Okay. But imagine that you have a term like 1/3 lambda phi cube plus again a tadpole generated perturbation theory and higher order terms. Okay, so this expansion is in powers of gs square. The potential that you calculate in perturbation theory, of course, has powers of gs square. But now, when you solve for v prime phi equal to 0, okay, you see that the phi starts at square root of minus c over lambda times g string plus higher order terms. Okay, so the expansion of the field is no longer in powers of gs square but in powers of gs. Okay. And all of these can be implemented here, because after all this is just a set of set of equations for psi vacuum. Okay. And in particular you can consider the case where you have integrated out most of the fields. So this is a finite number of variables now, right? You are looking at a finite number of equations in a finite number of variables. Okay, so you can solve it exactly in the way that I am doing here. Okay, here I am considering the case of one variable. Here I will have a multiple variables, but still a finite number of them. Okay. Now, when I said that in favorable cases, this basically means that we can solve it in the case where this has the right sign. Okay. You see that if phi is a real field and if c over lambda is positive, then this solution doesn't make sense, right? So you have to make sure that c over lambda is negative. Okay, so for certain choice of signs of c, we can find non-trivial solutions. Okay. And as I said, this kind of solution you cannot get in perturbation theory, the standard worldsheet perturbation theory, which always gives an expansion in powers of gs square. Okay, here, for example, when we work out the expansion, you will get terms, some of which will have terms of order gs.
In a superstring theory, like the heterotic kind of theory, such massless fields which are not moduli, they happen at very special points in in a compactification or something?
Well, yeah, you can call this a spatial point. For example, if you take isothertic to heterotic string on Calabi-Yau, standard Calabi-Yau, right, it typically has these massless fields. Right now, you can still say it's a spatial point because you can switch on torsion and maybe these massless fields will be lifted. But these are basically fields which are charged under some U1 gauge field. Okay? So they are not moduli because there's a D-term potential for these, okay? But they are massless. So these are like charged fields which are massless. So you're right that it's spatial in the sense that, I mean, you consider, for example, heterotic string compactification with left-right symmetric, right? You can, in general, switch on torsion and try to lift these fields. Okay, but for compactifications of this kind, there are plenty of massless fields that you can find.
And type 2 also into other examples like this?
Type 2, I don't know of a specific example, but with sufficiently complicated compactification, one can probably find such massless fields. Yes, so what happens is, so this is, I just gave this as an example, but this case of isothertic to heterotic on Calabi-Yau, right, the potential that one gets actually is not this, but it's more like 1/4 lambda phi to the 4 plus CGS square phi square, okay, something of this sort. So now let's put a half here. This is a one loop mass term that is generated. Okay, so now if you look at the field equations, we have lambda phi cube plus CGS square phi equal to 0. Okay. So you get three solutions. One is phi equal to 0, the other one is phi equal to plus minus square root of C over lambda times GS. Minus, yes. Okay. And for the known cases, this C actually turns out to be negative, so this solution makes sense. So there are three solutions at this level. At order GS level, there are three solutions. Okay. But what one finds is that this solution actually is non-supersymmetric. Okay, so this is like having a potential of this kind. Okay, because C is negative, right? So you can see that the phi equal to 0 is actually maximum of the potential. Okay. So this is a non-supersymmetric configuration. These are supersymmetric. Now, to this order, you don't see any difference, all are solutions. But once you go to one higher loop, you find that the dilaton acquires a tadpole at this vacuum, right? And that makes the solution inconsistent. Whereas here, the dilaton tadpole continues to vanish because they are supersymmetric. Okay? And you get a non-trivial solution. Okay, but the expansion around the new solution will be in powers of G string. So in this case, supersymmetry doesn't break. That supersymmetry would have broken at this vacuum, but not at these ones. Yeah, so phi goes to minus. In fact, it's, I mean, this is actually a complex field. So it's mod phi equal to this. So phi has a U1 symmetry that is broken like this. It's one charge scalar. Right? So basically, this potential comes from a D-term potential. So phi is charged under some U1 gauge field, right? And that's what gives rise to this potential. It's basically you it's all of these are elementary string states. So you calculate the spectrum in a Calabi-Yau background, and you find that there are these charge scalars which have this potential. Yeah. So this is like some kind of fixing of the U1.
Fixing of the U1, but not supersymmetry.
Not supersymmetry. The supersymmetry is not broken exactly. In fact, I don't think there is any example. I mean, this was first proposed as a possible candidate where supersymmetry could be broken. But in all examples that one knows, this C is negative. See, this you can see that if C was positive, then supersymmetry will be broken. Because then this potential will not be like this, but it will be like this, right? And the minimum would have been lifted. Okay, phi equal to 0 is always, so basically the full potential is something like mod phi square minus V square GS square square. Okay, so if this was positive, then supersymmetry would be broken at phi equal to 0. Right? Phi equal to 0 will be a minimum, but supersymmetry would be broken. But in all examples, one finds that this is actually negative, and hence supersymmetry is not broken.
When you say alpha is less than 2, I mean, so I can can see that if the potential is higher, then the powers will be less than 1.
Yeah, it's less, okay, maybe I should say it's less than 1, because I don't know of an example. I mean, you can cook up contrived examples, right, where
it begins with GS to the 4.
Exactly, that's right, yeah.
The 2 loops. So
exactly, yeah. So basically the point in these cases, the expansion is not in powers of GS square, right? That's the important point, that the expansion happens in some other part of G, and that's the signal that it's not the usual perturbation expansion. Okay, and the third case, which is the worst case, is that when you have the one-point function of moduli fields is non-zero. Okay, moduli fields by definition has no potential at tree level. Okay, so here V phi will be like CGS square phi, and in general there is no systematic perturbation expansion. Okay, so this, for example, has no solution. V prime phi equal to 0 has no solution, at least in a power series expansion in G string. It could still happen that for sufficiently large G string you may find a solution, but then you lose all perturbative control. Okay, so this is in this case we don't know what to do. No perturbative solution. What is the example of such cases? If you take a non-supersymmetric background, for example, typically at one loop you will generate a dilaton tadpole, right? And then there is no solution. Okay. So in any case, we will be considering the cases 1 or 2, okay, where we have a psi vacuum, okay, which has a perturbation expansion, and as I said, in principle, you can develop a perturbation theory to construct the psi vacuum. No, not that I know of. I mean, in all the known examples, so basically it's a question of determining whether this C is positive or negative, right? And in all the examples I know, C has the sign that makes restored supersymmetry. So I don't know whether there's a deep reason behind this, but at least in the known examples that seems to be the case.
It could be that all of them belong to the third example.
Yeah, exactly. They're completely runaway behavior, yeah.
If you start with some non-supersymmetric classical background and try to see whether there's a nearby solution, you would see that the corrections are large.
Exactly, yeah. So that of course is a typical situation, that if you have, if you start with a non-supersymmetric background, typically the dilaton will get a vacuum, will get a one-point function, right? And then you don't know that it's fixed. Right? There is no weak coupling solution. Okay, so now we go to the next step. Okay, so we assume from now on that we have found some psi vacuum by perturbation theory, and as I said, it's reasonably straightforward. Once you have constructed the perturbative series to any given power n G string, okay, you have a finite number of equations in a finite number of variables, so you just go ahead and solve them. Okay, and there is a standard perturbative technique to solve them, right? You start from psi vacuum equal to 0 and solve it iteratively.
So you do sometimes add a potential by hand, it is not perturbative, like in KKLP or something.
Yes, that's right. So then of course you don't really have much control, right? Because once you add non-perturbative terms, then you have to worry about whether you have to also take into account all the perturbative terms, right? Yeah, so you can do something which is not quite kosher in this language, right? That you add some non-perturbative term and try to see if there is a solution. But at least if you want to proceed fully systematically, right, then I think the only thing that you can do is when there is perturbative solution.
But this formalism, for example, does it allow us to calculate some kind of an instant on solution?
Well, the point is, if you can find the solution in string field theory, you could in principle expand around that instant on background and calculate the determinant, right? So you have to then understand how to represent. Suppose the instanton is a classical solution, right? That should be obtainable as a solution to this set of equations, right? And then I'm going to describe now how to expand around the classical solution, so that you can do. And then you can in principle quantize the theory around the classical solution and calculate, say, one loop determinant, right, using the string field theory language, which will give in principle not only the determinant of the massless field but also the full set of massive string spectrum. But to get a full non-perturbative effective field theory is difficult because you don't know whether the terms that you are ignoring, right, which is the whole perturbation expansion, whether those can be ignored or not, right? If you are including the instanton corrections, in principle you should also include all the perturbative corrections.
Would it be possible to incorporate in this something like background, an ADS background with the flux quantization?
Yeah, in principle it should be possible. The main problem in ADS background, see, RR background in this formalism is not a, not too much of a difficulty in the sense that you have the RR vertex operators, right? So you just switch on those fields. Okay. What is not completely clear from this perspective is because this formalism is in the momentum space. Right? Once you have a curved space-time, right? Suppose you have formulated a field theory in flat space-time, right, which is written in the momentum space. Right? And now, how to describe a curved space-time in that momentum space? That seems to be the main bottleneck.
But the momentum space, was it very essential for you?
No, it was not very essential, but for any practical calculations, right, you will calculate, for example, these. You calculate by calculating the correlation function of the Fourier modes, right, of the vertex operators which have the form e to the I k dot x. If you try to write the vertex operators in the position space, then in general it becomes very difficult to calculate the correlation functions.
In something like ADS5, you may be able to find the proxy for momentum.
That's right, yeah. So if you could do that, then you could try to reformulate this in ADS5 directly. Right? But suppose you have formulated the string field theory in flat space-time. Right? In supergravity, that's what you do, right? You have a supergravity that is formulated in flat space-time, and then you find a solution which is ADS. Right? That seems to be difficult, at least in this formalism, right? But maybe there is a way to rewrite this, right, which will make it simpler. But at least in the way string field theory action is written now, it seems hard to describe ADS because of this reason. Okay? Not so much the RR background, because RR background is weak anyway, right? So in the large radius limit, the local RR field strength, you can do a perturbation expansion. Right? And there are RR fields have specific vertex operators, so they are represented by specific modes in H hat, right? Which is H minus up, for example.
BRST, for the BRST operator, you would need to know the worldsheet CFP.
Yeah, but I'm saying that you formulate the theory in the flat background.
Oh, and then treat this as a...
Then treat this as a perturbation, right? So in that language, switching on RR background itself is not a problematic thing, because RR background corresponds to switching on certain fields, right? What seems to be problematic is how to describe curved space in this language. Right?
It is not any more complicated than just doing field theory on it. So even if you want to quantize some field theory, you want to like do it with modes and so on in a practical way.
Yeah, but I'm saying this is even earlier, that before you even talk about quantizing in the curved space background, suppose you want to find that curved space as a solution in the supergravity, right? Suppose you have taken the supergravity and expanded it in parts of h mu nu, right? Which is what this string field theory effectively does, right? It gives an expansion in parts of h mu nu. You write the theory as a field theory of h mu nu fields, and now you want to describe ADS background in terms of those h mu nus which are written in the flat space background. Right? Of course, you can do it, because after all, metric, once you got to get the metric, you can work out what h mu nu is. Right? There's a difference between the metric and g mu nu, and eta mu nu. But it's hard to describe supergravity as a solution in h mu nu space. Right? They describe ADS5 as a solution in h mu nu space.
So one way to do it would be to argue for supersymmetric solution.
That's right, yeah.
So the ADS5 plus H5
is a supersymmetric solution, yeah.
It does not get renormalized. I mean, up to the cosmological constant.
Yeah, that is true. But I'm saying even then, to even just at the level of supergravity, right? If you didn't write the supergravity in terms of the metric, but in terms of h mu nu, which is g mu nu minus eta mu nu, then h mu nu doesn't have a very simple form, right? It's a complicated function of x and t when you have the ADS background. And now if you try to rewrite it in the momentum space, right, it's even more complicated, right? It doesn't have any natural form at all. In fact, it's not even clear how to take the Fourier transform, because these h mu nu actually, it's as a function of x, it blows up, right? So in the Fourier space, it may not have good representation.
So that's why, I mean, I was wondering, well, it seems like a singular perturbation to go from flat space to ADS since you're changing the infinity.
Yeah.
So can one, okay, well, I can see that limits of ADS amplitude should go to flat space amplitude.
So locally, for example, one could try to do that, right? Suppose you start locally and you are trying to build the ADS, right, near a certain region, right? Suppose your ADS is nearly flat, right? You can always go to the locally flat coordinate system, right? In which case the h mu nu deviates from eta mu nu by a small amount, right? And then you can try to build a solution perturbatively. So that of course doesn't capture the global picture, right? But locally you may be able to get the solution. The existence of a solution of this kind, you may be able to see locally, right? But I think getting the global structure will be hard. Yeah, in Poincare ADS or something, you may be able to get something, yeah. But it's also possible that there will be a different formulation of this, right? Now it's written naturally in the momentum space, right? Because these are written in terms of correlation function on Riemann surfaces, and those, they are the momentum space vortex operators are the standard vortex operators which you know how to deal with, right? But it's possible in principle to rewrite this so that you really think of this as a position space wave function or position space fields, right? And then writing curved space background may not be very hard, right? Once you have gotten size as a function of the x and t rather than as a function of the momentum.
So that is like the vertex operator, the plane wave e to the power ik dot x.
Exactly.
By an appropriate wave.
That's right.
Vector of Laplace wave, function of Laplace wave.
Exactly. Yeah.
So yeah. You do that in position space. It's the bulk to boundary propagator which would be the appropriate this thing, and it's most naturally written in position space. So I guess you can write in terms of Bessel functions or something in terms of at least the parallel momentum.
Yeah, but the radial direction is the problematic case, right? Yeah. Yeah. The point, if one tries to write it in the position space, the problem is that those don't have nice conformal properties. So you have to calculate this vortex operator, and the correlation function depends on the conformal properties of these vortex operators, right? Because these are off-shell objects. And when you write things in a position space, right, they don't have nice conformal transformation properties. In general, the field theory will look very complicated when you write it in the position space.
Even if you write it in this embedding formalism, where you go 2 dimensions higher, 1 dimension higher.
Yeah, in one is that in string theory, of course, you don't know how to take into account that extra dimension, right? Because you always have to have the critical dimension. So you don't, so I don't know of a way by which you can think of string theory backgrounds as embedded in 1 dimension higher.
You have to, in the embedding space, you have to impose this hyperpolar.
Exactly.
Hyperpolar constraint.
That's right. Yeah.
These are many momenta which kind of play an analogous role. Though, of course, for each individual vertex operator, how to do it is still not
exactly. Yeah.
You can
take the whole S matrix. Yeah.
Variables you can write
exactly
for a given process, ki dot kj, but
yeah.
not individually ki.
Ki, yeah. Okay, so now the idea is that we take this solution and expand around psi vacuum. So we now define phi, which is psi minus psi vacuum. Okay, so these are the fluctuating fields, and similarly phi tilde, which is psi minus psi tilde vacuum, which is of course the same as psi tilde minus psi tilde vacuum, which is psi tilde minus psi vacuum, because in the NS sector psi tilde and psi are the same. Okay. And now let's expand the original 1pi action, okay, in terms of phi and phi tilde. Okay, these are the fluctuating fields. So this has the following structure. You have the S1pi of psi vacuum, psi tilde vacuum. Okay, so this is the original 1pi action evaluated in the background in the classical solution that we have found. Okay. And then plus, I'll write down the answer and then explain the various parts of it. Okay, so we can see two new quantities here. One is k, okay, which is an operator, and one is this double prime bracket. So I'll write down the definitions of these objects. So k on A is by definition over n Okay, so this is for A belonging to H hat T. Okay. And we define this to be 0 if A is outside H hat T. And this object A1 to AK or AM double prime So what I have done here is that I have substituted psi equal to psi vacuum plus phi, psi tilde equal to psi vacuum plus phi tilde, and expanded the original action. Okay. This is the action evaluated in the vacuum solution, okay, and these are the terms that depend on the fluctuating fields phi tilde and phi. Okay. So these two you can easily recognize comes from the kinetic term, original kinetic term. Okay. Now here, this is the quadratic part in phi, which comes from the interaction term. Originally there is an interaction term, okay, but the interaction term now we have expanded in part series of in psi vacuum, okay, and that gives a quadratic term in phi. Okay. There is a linear term in phi because by construction this is a solution to equations of motion. Right? So when you expand the action around the solution to equations of motion, you shouldn't get a linear term in the fluctuation. So there is no linear term. So like this is a quadratic piece. Okay. And then the cubic and higher order pieces are here, okay, which I have defined here. So this gets, of course, a contribution. The n equal to 0 term is the original interaction term. Okay. But now, because in the presence of psi vacuum, okay, you will also have all the other interaction terms, because if you had for example, psi to the some power n, right? Then of that n, you can take certain number to be some vacuum and the others to be the A's, to be the fluctuating fields. Okay, that's how you get this part. Okay. So this is a straightforward exercise. These are the definitions. Okay. Using this definition, one can easily verify that the original action expressed in terms of phi and phi tilde takes this form. Okay, and of course you have to use the fact that the psi vacuum satisfies classical equations of motion. Okay, that's why the linear term in phi goes away. Okay. Are there any questions? Okay, I'll now use two other definitions. So define QB hat equal to QB plus GK. Okay, so this one acts on H hat T, and QB tilde is QB plus KG. This acts on H tilde T. Okay. So again, I'll leave as an exercise to show that QB hat square is 0 and QB tilde square is equal to 0. Okay, this is a consequence of the following identity. Basically, what one can show that QBK plus KG, plus KQB plus KGK equal to 0. Okay, so the definition of K I have given here. Okay, K acting on any state A. Okay, so what you have to prove is that this quantity acting on any state A is identically 0. Okay, that's what goes in proving this. Okay, so you take any state A, okay, apply this combination, use this definition of K, which is here, okay, and use the fact that the psi vacuum satisfies the equation of motion. Okay, and the various identities we had derived involving these curly brackets. Okay, and using that, one can explicitly prove this is true, and as a consequence of this, these two are also true. Okay. So we'll see that this object QB hat in fact plays the role of the new kind of BRST operator. You can call this a renormalized BRST operator, okay, which takes into account the effect of the quantum corrections. Nevertheless, it is something that squares to 0, okay, as long as psi vacuum satisfies equations of motion. Is this clear? So another exercise. So again, it's straightforward algebra. Okay, in fact, that's what as I said, you never have to go back to the Riemann surface picture. All of these are just pure algebra. Okay, we can prove them based on the identities that we had already written down earlier. Okay.
These are the two that will enter for phi tilde and phi.
Yeah, these are the, well, actually this QB tilde will not really enter phi tilde and phi. The point is the transpose of QB tilde and, okay. See, if you look at K, right, what K does is that K acts naturally on a state in H tilde, H hat, and gives a state in H tilde. Okay, because if you look at the definition of K, this one belongs to H tilde. As we had said, the square bracket actually gives you something in H tilde. Okay. So K maps from H hat to H tilde. Okay. Whereas QB tilde and QB hat should both map from either H hat to H hat or H tilde to H tilde. Right? It shouldn't change the picture number. Okay. So because K acts naturally on states in H hat. Okay. Yeah, so QB tilde acts on H tilde because if you start with H tilde, right, you cannot act K directly, right? You have to first act G to bring it into a state in H hat, that's the picture changing operator, then you can apply K. Okay. On the other hand, if you have QB hat, right, you can see that, I think I made a, no, this is fine, yeah. So QB hat should act on states in H hat, right, and give you back states in H hat. But K acting on state in H hat, give you back a state in H tilde, right, and you have to bring it back to a state in H hat, and that is done by G. Right, so it's the nature of K that makes this QB hat and QB tilde slightly different, right? That once, in one case you have to first change picture, then apply K, right? In the other case you have to first apply K, then change picture. And these are in some sense transposes of each other, right? Because since -3 picture and -1/2 picture are paired, you QB tilde, right, will be the transpose of QB hat, right? And that's what you see, that if you transpose of that, then G goes to the right.
K does not have any analog usual perturbation theory.
No. Well, K is basically the effect of the two-point functions. You generate extra two-point functions once you go to the loop level, right? And now K is the contribute, so that should contribute to the kinetic operator, right? And K is that object. Right? But in the usual perturbation theory, of course, you don't try to resum, you put it in the kinetic operator and rediagonalize, right? You just sum over all possible terms, and that's where the mass renormation problems come in. Because you keep inserting these two-point functions on the external leg, right? And you don't have any way to resum, right? Whereas here, we put K as part of the kinetic term, right? And then we can just invert the kinetic term as a whole. Yeah, that in fact is the main reason why we want to do string field theory. That in usual perturbation theory, the analog of K will be these two-point functions which can be inserted arbitrary number of times on the external line.
Self-energy.
Self-energy corrections. So K is like the self-energy correction.
So alternatively, we can just define some operator K which just acts differently on H hat and H tilde.
That's right.
And takes it to.
Yeah, you could. So you can define Kg as your K hat acting on H tilde, right? And Gk as your K hat acting on H hat, and then it will be the same form, exactly.
Or you can take one operator which acts both on H tilde plus H hat.
That's right, yeah, that also you can do. So K hat will be defined as Gk on H hat and Kg on H tilde, yeah. But the point is, this is a really important one, right? Because our interacting fields are all in H hat, right? So this will play, only auxiliary role, as we'll see.
G also depends on what state you're at. It's an identity.
Yeah, so in the Nebu-Schwarz sector, of course, G is identity. So there is no difference between QB hat and QB tilde, right? If G is identity, then they are the same. So this difference comes in the Raman sector. Okay, so this identity is hard up to give. Yes. Yes, double prime. Thank you.
Okay, obvious, but A has some picture number.
A?
A has some picture number.
Well, K is an operator, right? So its mapping,
Changes the picture.
it changes the picture. It changes the picture by -1, right? And that's why G has to act to compensate for it, because QB hat shouldn't have a picture number.
So it acts like some anti-picture thing.
Exactly, yeah. It acts as some anti-picture changing operator, but it shouldn't really be called as anti-picture changing because this is coming from the loop levels, right? It's not something that you act on the sphere. It has GS square. K, for example, is already of order GS square. But it does carry a picture number.
C for the definition of stereo is like a picture number.
Yeah, okay. See, this object, as we discussed, that A has picture, suppose A acts on H hat, is in H hat T, right? So this has picture number -12. Let's look at the Raman sector. Okay. This, of course, has picture number -1, but that gets cancelled by various picture changing operators. So it has a, so net picture number of this, okay, is -3/2, because its inner product with a -12 picture, okay, is given in terms of curly brackets. Inside the curly bracket, all insertions have naturally picture number -12, right, or -1. Let's look at the Raman sector. All have -12, right? So this is defined by specifying its inner product with a -12 picture state, right?
Because it is phi r.
Because it's phi r, which is in -12 picture, right? Because otherwise, inside the curly bracket, because all the states are in H hat, right? It doesn't make sense to insert a -3/2 picture state here. So phi r is naturally in -12 picture, and that means that this square bracket must be -3/2, because those are conjugates to each other.
Okay, so all the square brackets are picture changing.
Exactly. All the picture square brackets are either in -3/2 or -1 sector. So they are in H tilde. Okay. Whereas the arguments of the square bracket are naturally in H hat. Right? We define it only for H hat.
So this is true for all the square brackets we had yesterday.
Exactly. Yeah. Okay. So this identity, you recognize that it's very similar. In fact, it's exactly identical to what we had earlier for the usual curly bracket. The only difference is that the QB hat there was QB and the double primes were not there. Okay, otherwise it's exactly what we had. Okay. And that will be useful because that means that the kind of identities that we are using there, okay, now we can use with respect to using the double prime brackets and QB hat.
Vanishing for n equal to 1 and 2.
Exactly, yeah. So those correction terms are basically in this K. This QB hat has the K, right? So that n equal to 2 term has gone into this K. And again, to prove this, you have to use the fact that psi vacuum satisfies equations of motion. Yes.
This in particular says that you can use QB hat and QB tilde to show that BV master equation is satisfied.
Yes, in this case, I'll write on the gauge transformation. Right? In this case, the BV master equation also implies gauge invariance, because now since you have to only tree-level calculation with these, right? The major problem is not there. Normally, BV master equation says that it's almost gauge invariant, but there are some corrections, right? But this satisfies what is called classical BV master equation. Right? Exactly, S, S equal to 0, and that follows as a consequence of these. Okay. Equivalently, I can say that there is gauge symmetry. So the gauge symmetry takes the following form: delta phi maybe I should have defined that. Okay, I'll do that. So the K lambda term is basically the n equal to 0 term here. Okay. And the definition of Okay, it's simply that if you take phi r C naught minus yes, it's QB. Because the point is the lambda tilde gauge transformation doesn't get any corrections from loops. Because it's just like the psi tilde doesn't interact, right? Lambda tilde also gives a, yeah. Yeah, so the lambda tilde essentially is a gauge transformation of phi tilde, right? So this doesn't get anomalous at all. This is still QB. Okay, naively one would have thought that maybe it's QB tilde, okay, but it's not QB tilde because I mean the same way you can see here, right? Naively you might have thought that here it will be QB will be replaced by QB tilde, right? But that's not the case. Okay, the kinetic term is gets correct. This K corrects only the phi kinetic term, but phi tilde terms are still the same.
Why does one of them have a 1 by n factorial?
Oh, both of them should have. This is also 1 over n factorial. Thank you. Okay, now so far QB hat hasn't entered, but let me now explain why QB hat is important. And for this you have to look at equation of motion. So these have the form of QB okay, this n of course starts from 2 to infinity. Okay, and again one can try to massage this a little bit. Okay, so if we call this 1 and 2, okay, then g times 2, g acting on 2 minus 1, okay, gives you the equation QB phi plus G K phi plus okay. So the idea now is that this is the interacting field equation. So phi is the interacting field. Okay, that gives the actual string theory S matrix. Okay, sorry, G multiplying it. Thank you. Okay. So this is the interacting field, and once you have gotten a solution to these equations, okay, we see that the only freedom that you have in phi tilde, okay, given for given phi, is to add solutions to the free field equation of motion, which is QB phi tilde equal to 0. Okay, so that just gives a solution to the free field equations of motion. So phi tilde is free, phi is the interacting field. Okay, and that's also of course apparent from the action itself, okay, where you can see that the interaction term involves only phi.
This is very odd from this point of view of this ADS type deformation. If we consider, even assuming in principle you can do it somehow, it would seem that then there is something, a set of fields which are like massless fields of flat space
Yeah.
In addition to
that is true.
field
Yeah.
of the ADS space,
Yeah.
the QB
Yeah.
is.
Yeah.
So these would be of course, probably it's only perturbation theory that.
Yeah, somehow the point is that the phi tilde, I mean, I have not understood the role of phi tilde. I mean, phi tilde seems to be just purely an auxiliary construct which lets you write an action, right? If, for example, you didn't care about the action, right, but only about the equation of motion, then you could have written down this equation and forgotten about phi tilde altogether, right? It's only if you want to write down an action that you need the help of phi tilde. Yeah, and the point is that, okay, I mean, what you could do in principle, okay, is that at this stage you could change this QB to QB tilde, right? Suppose you just declare that I'll consider another auxiliary system, okay, where this equation, which will give this equation plus another set of free fields, but not free fields of QB, but of QB tilde, okay? So as far as the interacting part of the theory is concerned, it will give the exactly same equations. Right, but it will change QB to QB tilde, right?
Some constant piece.
Yeah, so that basically corresponds to in this action, right? You will, what you will do is that you will replace this QB by QB tilde. Sorry, this QB will still remain as QB hat, okay? Because there is a G already, right? G converts, so QB hat G is basically G QB tilde, right? From that definition. So you will basically change, you remove this piece, right, and change this to QB hat and this to QB hat. Okay, that will have exactly the same interacting field equations, but the free field part will have a different kinetic operator. Yes, that
there's nothing to choose.
There is nothing to choose because the free fields are not observable anyway. So in principle, you could just change it. Is that that's not something you will get starting from the original string field theory action and integrating out fields. Okay, now we come to the second main point, okay, why string field theory is useful, which is that now suppose, so this is the equation for the fluctuating field, right? So let's look at the linearized equations of motion. Linearized equation of motion for phi, which is QB hat phi equal to 0. Right? Because these are nonlinear terms, n equal to 2 to infinity. Why is this important? Because these solutions to these will occur at some specific values of momentum. So if this has a solution, if there exists a solution at momentum k, okay, this is a momentum that is carried by this phi, then minus k square is the renormalized mass square. Okay, this is the way you find renormalized mass square in this here. In the tree level, QB hat is QB, right? And there, as we know, the solutions to QB phi equal to 0, okay, are the physical states. Okay, and wherever you find physical states, that gives rise to the physical mass square. Now, exactly as in the case of tree level system, okay, not all solutions are physical, some are pure gauge, right? We know that if phi is of the form QB times lambda, right, that's a pure gauge solution, right? You shouldn't count those. The same goes here. Okay. Trivial solutions, which are pure gauge, trivial solution are of the form phi equal to QB hat lambda. Okay, why is this a trivial solution? Because QB hat square is 0, right? Which is what I had said here. QB hat square is 0. Okay. So any state of the form QB hat lambda is automatically a solution to this equation, but those you have to quotient by. Okay. Once you have removed those, okay, then you will find that the other solutions, okay, occur only for specific values of momentum, okay, and then value of k square or value of minus k square gives the mass square of the physical state, and this is the renormalized mass square. Is that clear? Right? Because this is the linearized equation of motion of the 1 pi effective action, right? Where you have already taken into account all the quantum corrections.
Do you think the linearized from the delta of phi, the linearized term would also get an n equal to 1 term, g phi lambda? Why is it not there?
Well, that is this term. The 1-point function basically has gone into the definition of k.
No, I'm saying for the trivial things which are too exact. If you look at the gauge transformation.
Yes.
Of delta phi.
Delta phi, yes.
And just say you just keep linear terms of phi. Would you also get the first term that
N equal to 0 term.
n equal to 1 term?
N equal to 1 term is not linear, right? Meaning it's phi times lambda. So we normally call it non-linear. It's like if you have gauge field, right? The linear term is what we call just the phi independent term.
Just like d lambda.
Yeah, this d lambda and this is the a, lambda times a term, right? Lambda times a term. So that we don't count in the linearized gauge transformation, right? Linearized, when you think of linearized gauge, when you declare what is pure gauge, you just look at the constant piece, the phi independent piece. Becomes yeah, exactly. You'll get an extra factor of G string. Okay, so this is, I mean, this may look formal, but as I have already said, that you can, if you work with the field theory where I have integrated out most of the degrees of freedom, okay, then QB hat, in fact, for a given momentum, QB hat is a finite dimensional matrix. Okay, so this is a perfectly solvable problem. We have a finite dimensional matrix, and you are looking for its 0 eigenvalues. Okay. What of course you have to do is to look for not exactly 0 eigenvalues. If you work to a given order in G string, right, you demand that the eigenvalue is 0, that QB hat phi is 0, okay, up to corrections of order G string to one higher power. Okay, because QB hat square, for example, will not be exactly 0 if you have truncated it, right? It will be 0 plus up to corrections of order that you have not taken into account. Okay, so that's the only thing you have to keep in mind. But otherwise, it's a finite dimensional matrix problem which you can solve in principle once you have gotten this operator QB hat to a given order in perturbation theory. And this is the way you determine the renormalized mass. Okay, are there questions? Okay, so I'll describe later how to define perturbation theory. In particular, we have to now calculate propagator with this action now. Okay, but before we do that, let me just give a simple illustration of how this formalism may be useful, okay, to prove some simple results. Yes.
Which was not propagating at tree level. Could it be that it gets a kinetic term and then?
Yes, it could be, but I mean, there is a way to set up this perturbation theory where you solve it as a perturbation expansion in G string square, right? So the mass square gets correction to first order and then order G string square and so on. If there's an auxiliary field kind of term, right, then you may get a formal solution, but that formal solution, for example, will be non-perturbative in G string, right? So you will recognize that from that effect, because the kinetic term now will get contribution from order G string square, right? Yeah, whereas at the tree level you have a constant piece, right? So you'll get a 1 over G square kind of square. So you can recognize it by, I mean, you can throw away those by solving it perturbatively.
You can throw away that.
If you start by solving the equations perturbatively, right, instead of trying to invert the whole matrix at one go, right? Then that perturbative scheme automatically doesn't take into account these, right? Because you set up the problem so that you look for m square, which is some original m square which was there at tree level and small corrections, right? So, and then you, at each stage you solve for, by comparing coefficients of G string square on both sides, right? So if you proceed that way, then you will never see these spurious solutions. Because from the beginning you are demanding that the m square starts at the tree level value plus corrections.
But supposing you didn't know and you were diagonalizing this matrix.
Yeah, then you will get this
something which had the eigenvalue, when you try to solve for this condition, you will get
some 1 over G string square kind of mass, right?
So what would you then say that somehow the perturbation theory is breaking down? I mean,
well, yeah, those are spurious. Okay, those are non-perturbatively heavy state, right? So you cannot trust those in perturbation theory, right? And what could happen is that at the next order, that state could jump, right? It could get large corrections. So it's not. It's just a. I mean, some sickness of perturbation theory.
So you throw those.
You throw those away in doing this. You only accept those solutions which are perturbative. I mean, the point is, if you could get QB hat non-perturbatively, right, then of course you have to accept all solutions, right? But because you are constructing QB hat in perturbation theory, right, you cannot accept solutions which have mass square of order 1 over G string square.
And also, I guess, even if both the mass and this thing were also of order 1, also it would still be little probably not clear. I mean, if both the kinetic and the mass term were generated at order G string square,
yeah,
then in principle you can have a non-zero value of
that is true
of the mass square at something of order 1.
Yeah, but again, those are not acceptable. Yeah, because you only accept those which are actually close to the tree level value, right? That in the G string goes to 0 limit, they should go back to what their original spectrum was.
The perturbation theory is not good.
Yeah,
Giving you some new state.
exactly. Yeah.
Yeah, so you're getting propagating states.
Exactly, yeah. Yeah. Okay, so before I describe perturbation theory, let me just give a simple example, which is to see how in this formalism we can show that unbroken supersymmetry implies Bose form degeneracy. Okay, in fact, I'll do a little more than proving just Bose form degeneracy. We'll also see that when the states are unstable, okay, unbroken supersymmetry means that the bosons and fermion pairs have the same width.
That is the statement that even imaginary part of the.
Yeah, that imaginary parts will be the same. Okay, so first let's see what we mean by unbroken supersymmetry, right? What is the signature of unbroken supersymmetry in this formalism? Okay, so for this, let's recall that we have the lambda gauge transformation, which probably I just erased. Oh, it's still there. So forget about the lambda tilde, which is trivial. Lambda gauge transformation is delta phi is QB hat lambda plus order phi and delta phi tilde order phi. Okay. So this is gauge symmetry. Okay. Now we'll say that the lambda generates a global symmetry, okay, which means it's unbroken gauge symmetry. So lambda generates global SUSY, generates global symmetry. If QB hat lambda is 0. Because if QB hat lambda is 0, then delta phi doesn't have any homogeneous term, right? Its transformation starts at order phi, right? Which is the way a global symmetry acts, right? Whereas a gauge symmetry always shifts the gauge field by a constant piece, right? It's like if you have ordinary U1 gauge symmetry, right? Delta mu equal to del mu lambda. Okay. Which part of lambda is global symmetry? That's the lambda equal to constant piece, right? Because the del mu lambda term vanishes. You still have the higher order terms, okay? Lambda fi, the f abc lambda ab, right? That term is still there. Okay. So constant lambda degenerates gauge symmetry because it's this part vanishes, okay? The inhomogeneous piece. So this is a general definition of an unbroken global symmetry, okay? And it's a unbroken global SUSY. Unbroken global SUSY if lambda belongs to H minus half. Okay, that's the Ramond sector. Okay, so let's suppose we have such a symmetry. Okay. Now suppose A is a solution to linearized equation of motion. Okay, which means QB hat A equal to 0. Okay, and this occurs typically at certain value of k square. That gives the mass square. Okay, I should have said here that here, when you're looking for unbroken supersymmetry, you are looking at the k equal to 0 sector. These carry 0 momentum. Okay, because typical unbroken supersymmetry comes in the translation invariant sector. This in general carries momentum, okay, some solution to linearized equation of motion giving a physical state. Okay, these could be bosonic or fermionic, we are not making any commitment right now. Now the claim is that QB tilde acting on lambda A is 0. Okay, how do we see this? We have to take the inner product. So to see this, take arbitrary basis state. So we have, so the left hand side is phi r C naught minus okay, I want to show that the inner product of this with arbitrary state vanishes. So we calculate the inner product with this phi r C naught minus QB tilde lambda. This I told you earlier that QB tilde, okay, is actually the transpose of QB hat. Okay, QB tilde has QB, and then there is a, in this you have a KG, right? QB hat is gk. So this you can check that it's given by QB hat phi r C naught minus lambda a. Okay, up to sign. The sign comes because you have to take this QB through phi r, okay, but it doesn't matter. So this is, oh, sorry, this is, there's a double prime. This is very important, okay, not, okay, I'm using the double prime bracket. So this is QB hat phi r. By definition, right? This square bracket was defined so that the inner product with any state is given by this curly bracket. Is this clear? Okay. Now we use the identity that this satisfies, that if QB hat acts one in turn on each of them, okay, the result is given by right hand side, okay, which is a sum of partitions. Okay. In this case, we can easily verify that the right hand side is 0, okay, because there are only 3 elements, right? You cannot partition it, okay, because you have to have at least 2 on one side, 2 on the other side, because this double prime bracket requires 3 terms. Okay. One term is provided by the basis states, those phi r and phi s, but you need at least 2 from one on one side, 2 on the other side. So unless you have 4 states here, okay, the right hand side is 0. Okay. So what you are left with is a term involving phi r QB hat lambda a and phi r lambda QB hat a. But QB hat lambda is 0, QB hat a is 0. Okay. So that basically shows that this is 0. Okay, if it's too quick, you can just go through it, right, and apply the identity, and you will easily figure out that this is true. Okay, and that means this is true. But if this is true, then we can apply G on this G QB tilde lambda a double prime equal to 0. Okay, and this means this is QB hat G lambda a double prime is 0. Yes.
So the K lambda piece here in this, the thing that you were just erasing.
Yes.
In delta phi tilde.
Okay. Yes.
So what happened to the K lambda piece there in the gauge transformation?
Here there is a
The delta of phi tilde.
delta of phi tilde. Yeah, I think that K lambda piece. Okay, maybe the K lambda piece is not there. I'll check that. Okay, I think the delta of phi tilde will be identical to 0, but I'll check that. Yeah, but the point is, okay, even if delta phi tilde contains a shift, phi tilde is a non-interacting field anyway, right? So what is important is that the phi transformation should have no non-linear term, right? The phi tilde transformation doesn't matter, but I'll check if it is there or not. Okay, so this implies that if A is a solution to linearized equation of motion, then G on lambda a double prime is also a solution to linearized equation of motion, but at same k. Okay, at same k, because lambda carries no momentum, right? Lambda has 0 momentum. So these are exactly the same momentum as this one. But now you see that because lambda is in the Ramond sector, right? If A is bosonic, then this is a fermionic field, fermionic solution, and if A is fermionic, this is bosonic. Okay? So this operation then is pairing a bosonic solution to linearized equation of motion to the fermionic solution to the linearized equation of motion exactly at the same momentum. Okay? And that momentum is the physical mass square of the, or the k minus k square is the physical mass square of the corresponding state. So this shows that there is pairing, these pairs, solutions of the same mass square. Okay? And this is even if the solution is complex, right? We have not assumed anywhere that the k has to be real. Okay? So if, for example, the mass square had acquired an imaginary part, as what happens for a unstable particle, okay, then in general the solution will be for complex k square because the mass square has gotten an imaginary part, but this pairing would still hold. Okay? This then shows that not only the mass squares of the renormalized mass squares of the bosons and fermions are equal, but their widths are also equal, okay, as long as supersymmetry pairs them.
Vacuum will be something where lambda times A is 0. If the
That's that, yes.
annihilated, then,
Yeah.
Then of course the vacuum will be.
Yeah, basically the vacuum in this language will be A equal to 0 because you have already shifted fields, right? So yes, so the corresponding superpartner will be 0, and that's the statement that this QB hat A, QB hat lambda is 0, right? It doesn't shift the vacuum. So if you start with the vacuum solution, it just doesn't shift the vacuum solution.
And I was just wondering, because the vacuum solution
is not paired, exactly.
Not paired.
Yeah, yeah. Yeah, so the A by definition is not one of the vacuum solutions. I mean, vacuum solution will be A equal to 0 in this language.
Lambda
Will be also 0. Yeah. Okay, so now I just describe briefly the perturbation theory around the shifted vacuum and then I'll stop. Any of the global symmetries? Yes. So any of the global symmetries will also pair like this. Exactly. So this, I mean, I used here lambda as the supersymmetric transformation, but it's true also for other global symmetries. I mean, for supersymmetry, it's somewhat non-trivial because it's not easily visible, right? It basically comes from a Ramond sector, whereas normally other global symmetries are realized as some symmetry of the world sheet theory. So you see it explicitly as a symmetry of the conformal field theory. Okay. So we can work in the Siegel gauge.
So, but does this help you to construct the supercharge, or even in general the global charge? Can one use this to construct that?
Well, it can be used to construct what is called a supersymmetric word identity. Is it how the various fields transform under supersymmetry and the corresponding word identities. Now, to construct supercharge, you need a Hamiltonian formulation, right? Because it's not clear how to go from here to the Hamiltonian formulation. Right? But it can be used to say how the various fields are transforming under supersymmetric transformation. Okay, so you use Siegel gauge again, B naught plus phi equal to 0, B naught plus phi tilde equal to 0. Okay, and in that case, the kinetic term Okay, so you have to invert the kinetic operator. So the kinetic operator is C naught minus C naught plus L naught plus G C naught plus L naught plus okay, I have written down that in a phi tilde language. So this is phi tilde phi, and on this side it's phi tilde phi. So the propagator will be its inverse. Okay. And that typically has the following structure. Let me write it down: delta f check, delta f bar, okay. So you can find all of these operators. I'll just write this one because this is the relevant one. Okay. So exercise is to show that delta f is G it can be written these two different ways. Okay. You can of course expand it out, okay, in power series in k, because k is of order gs square. Okay. But that will correspond to having representing the propagator as by inserting self energies, okay, which is precisely what we want to avoid, right? Because if you insert self energies, okay, then on the external line it doesn't make sense. Okay, so you really have to work with the full propagator. Okay, and again, if you are working with this finite dimensional subspace, okay, where there are only a finite number of fields, then this is a finite dimensional matrix, right? So you can in principle invert it, and that's what we do. So this is the propagator. Okay. And the reason that I have picked only this part, okay, and so I'll also leave it as an exercise to find other entries. Okay. And again, that this psi propagator, or phi propagator in this case, phi is the interacting field, will only involve delta f. Okay, so from a 1 pi vortex, we'll have a phi coming out, okay, another vortex, phi here, so it's delta f which will be here. So another exercise is to show that the following identity is true. Okay, note that it's QB tilde here, okay, effectively reflecting that here QB hat is acting from the left, here because it's acting from the right, okay, you have to take the transpose, and that's why it's QB tilde. Okay. So this is the analog of QB Okay, remember that this identity played a crucial role in deriving the word identity. Okay, the similar role will be played by this identity over here. Okay. So now let me just write down the word identity and then I'll stop. So let's now define gamma A1 to n is Green's function, truncated Green's function. Okay, and truncated here will mean that the full external propagator truncated. Okay, this is what will enter the LSE procedure, right? Because earlier we had defined this G where you had truncated only the tree-level external propagator. Okay? But that of course had the problem that it didn't have an on-shell limit, right? Because if you try to take the on-shell limit, the intermediate states will start going on-shell. Okay? Here, you just remove the full external propagators. Okay? So G in principle will contain a Feynman diagram of this 1-pi effective field theory. Okay? Where these are delta F. Okay, the phi propagator, and these are not there. You cut out all the external legs. Okay, and the idea is that this is what will directly go in the LSD formula. Okay, because LSD formula will use this multiplied by some appropriate wave function normalization factor to get this matrix. Okay. So then by construction, this gamma will have no divergence in the on-shell limit. Okay, where an on-shell here will correspond to external states which are QB hat invariant, not QB invariant. Okay, because that's the new definition of on-shell external states, right? Because QB hat is the new, the linearized equations of motion that we have now is QB hat phi equal to 0. So final exercise is to show that this identity is true. Okay, and the way you will prove this is again that you take QB hat, okay, you are applying QB hat on all the external legs, okay, but you also apply on the internal legs. Okay, so when you apply QB hat on the external legs, or sorry, on all the vortices, okay, then you can use the identity that the double prime vortex satisfies, right? Double prime vortexes are the vortices of this theory. Okay. That will generate a set of terms which are the analog of the first terms that appeared in the word identity for G. Right? You remember the first term came from applying the word identity. Now there is no analog of the second term, right? Because the identity that phi r satisfies, let me remind you that the double prime satisfies A1 to n Okay, so you apply this identity on each vortex. Okay, And for that, you have to add some extra terms because you are also applying QB hat on the internal lines. Okay, that gives you a set of terms. Okay, so in this side, on the left hand side, it will give a set of terms where this is replaced by gamma, this is replaced by gamma. Okay. Then you have to take into account the fact that we have applied QB hat on the internal lines, which have to be subtracted out. Okay. And that is done by using this formula. Okay. And you can show that what you subtract out is exactly something that cancels the analog of this term, okay, with this double prime replaced by gamma. Okay, so maybe I can write down that step once and then I'll stop. So what we will get is the sum over I equal to 1 to n the first term will be minus okay, so this is what you get by applying the word identity directly and using this formula. Okay. And then you get another set of terms Okay, this is coming from the fact that you have overdone this applying QB hat. Okay, you have to subtract off the cases where QB hat now acts on the internal lines. Okay, that gives this anti-commutator of QB hat with the propagators. Okay. Now you use the fact that this is given by G, use this identity, and you see that these two terms cancel. Okay, so this is 0. So this is the word identity, okay, that we'll use. Okay, in fact, one simple application of this word identity is that if, say, all but one states are physical, that means they are annihilated by QB hat, and one of them is pure gauge, okay, of the form QB hat lambda, okay, then this identity implies that the S matrix of all n-1 physical states and one pure gauge state is symmetric. Right, because you can transfer the QB hat on the physical states and those just annihilate the physical states. Okay, so gamma of A1 to an-1 QB hat lambda is 0 if QB hat I equal to 0. Right, so this is the immediate consequence of this identity. Yes.
How do you get QB tilde? I understand that there should be QB.
Oh, QB tilde because it's QB hat acting on this set, you transpose it, that's why you get QB tilde. Right? So it will be QB hat acting on this side, right? But because you are writing it as an operator, right? Everything is acting on the right. That's why it's QB tilde. Because instead of writing QB tilde, we could have just written QB hat transpose. Okay, for QB it didn't matter. We could write QB, but here because of this K and G being coming in the opposite order, you have to be a little more careful. So the fact that it's QB tilde, not QB hat is not really very significant. It's just the way it acts. Okay, so we'll see that this word identity will also be useful. This more general word identity, okay, will be useful for proving unitarity. Okay, so I think today I'll stop here.
Coming back to the earlier question about the global charge, I mean, normally in a field theory, if we have an action formulation, we can at least construct the Noether current. So,
Yeah, okay.
But here, presumably, that's also difficult because you need to get some del mu j mu, the analog of the del mu j mu.
Yeah, that may be possible here. I'm just thinking. Because this is a regular symmetry of the action, right? You transform by this operation and you get a symmetry. So you can probably get a global current from here.
But normally, you need a local sort of, don't you need a kind of a local formulation in terms of some integral dx, and then you pick out the density?
Yeah, the point is, in principle here you can expand in derivatives. Right, so you could get local current by that procedure. Because once you have gotten the 1pi action, right, then you don't really care about having even an exponential suppression, because now you are not doing any loops anymore. Right, so all derivatives you can just expand out. And using that we can probably get a local current. But okay, I have not really thought about it in much detail. For the master action, you shouldn't really expand out the exponentials, because those are the ones which provide you UV finiteness. Right? Otherwise, it will be very difficult to see why the loops are UV finite. But at the level of the 1pi action, that's not necessary anymore, right? Because you have already taken into account all the loops.